Okay. Good morning, everybody. Do you see my screen?
Yeah, good morning. We are seeing it.
Oh, okay. Thank you. So, welcome back on a Sunday morning. Today, the strength seems to be encouraging. Last time we were only 5 or 6. Today we see 7. It's a good sign. Okay, so last week, we discussed from the Renaissance, that is after the Dark Ages, how the science shifted from Greek or Indian subcontinent to Europe-centric development. We started talking about Roger Bacon, who was the first, the first Renaissance scientists who talked about checking everything empirically, experimentally, and started questions Aristotle's authority-based science. Then we saw Copernicus proposed the heliocentric model, in which the sun is at the center and all other planets circle around the sun in a circular path, right? That was one of the fundamental shift from geocentric model. And then came Galileo, who improved the telescope, started focusing on the heavenly bodies. Galileo was another experimental scientist who either you experimentally verify or mathematically verify all this current science, the way the science we do now. It all starts from Galileo's method of doing science. So Galileo pointed this telescope in the heavenly to the heavenly body, and he told that even moon is like Earth, like a terrestrial body where lot of mountains, stones, hills are all there, right? And then he also wrote based on the Copernican model. Copernicus was, though he proposed the model, he could not see his book printed. He received the copy of the printed book on the day of his death. So he kind of escaped from the church authority. But Galileo published a book called Dialogue Concerning the Two World Systems, in which Galileo supports Copernicus model, but he does not say that straightforward in this book. In this book, in that book, which has three characters. They talk to each other. They kind of go into debate. One will support Copernicus model. Another will support. One will support um, geocentric. Another will support heliocentric. Third person will just ask questions. The debate will go on like this. Eventually, the reader who reads the book, he or she will get what is Galileo trying to say. So that is how this book is written. Though Galileo was a famous scientist at that time itself, he still launched or got into trouble because of his this book, Dialogue Concerning Two World System. So he was given a sentence that he is leading youth in the wrong direction, right? Because how can the earth, which is created by God, cannot be at the center of universe? How can something else can be center of universe? Anybody against this ideology was against church, right? So Galileo was sentenced to house arrest, and even during in the house arrest, he published his books and set the stage for further scientists to come and create further revolutionary ideas. In the meantime, Galileo's contemporaries, two of them, one is Tycho Brahe or Barkey, people pronounce it differently. He's one of the last astronomer without telescope. He observed the heavenly bodies, completely documented it accurately. But he could not interpret the document and put it in some kind of theoretical framework, right? So he met the mathematician Kepler. Kepler put these details in a nice theoretical form, where based on these calculations, he arrived at this Kepler's three law of more planetary motions, right? You all read this during your college days, right? I'm just checking who has joined. Okay, so Kepler's three law of motions was published. So where in one of the fundamental difference from Copernicus model is it is not just circular orbit, it is elliptical, but almost circular. But Sun is at the one of the centers. Right, ellipse has two centers. Sun is at the one of the centers, and all planets travel around the Sun in an elliptical orbit. And then to also cover the distance when the Sun is closer to Earth, because it's elliptical, right? At some point, Sun will closer to the planets. To cover the distance or to be against that attraction, it has to travel faster when it is closer to the Sun. So we just noted that in a video document last week. So these are the laws that set by Kepler, fit it into a mathematical model and gave to us. So that is where we stop. So let us proceed. Any other comments, question from last session? Okay. So we will proceed. So Newton comes now. We all know, everybody, even from the childhood, people have heard about Newton. Newton born in the year 1642, the year when the year that Galileo died. So people say that Galileo reborn again to complete his work, right? Um, so that's kind of continuation is there. So Galileo already did a lot of mathematical framework that helped Newton to arrive at his laws of motion, right? His three laws of motion is very famous, we all know. He talked about this, everybody continues in its state, right? It's first law. It says everybody continues in its states unless external force is applied. That is, a body, whether it's in rest or in motion, will continue in its state unless there is an external force applied. So it will just continue, right? We usually think that when it is in motion, some energy is spent or some to just put it in. Of course, we have to put the body in motion, we have to give additional force. But once it is in motion, if there is no external forces, it will continue in its state. So this is like kind of it's kind of people interpret it nicely that it shows the laziness of nature, right? You cannot change the state of something without an external force. So people call it inertia, or laziness of the world. And then that is the first law. And then that force that you want to apply to move that object is proportional to the mass of that object. This all we already know. And of course, the third law is very famous. Every action has an equal and opposite reaction in its popular form. We know that. So this is, he framed this laws. Of course, these are all already, Galileo did a lot of work on this, but Newton gave is like a package nicely. Additionally, Newton's another major contribution is is gravity law, right? We all know that when there are two objects, M1, M2, they both attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of the distance. This formula is very well known, and based on the mass, size of the mass, amount of the mass they attract. And then if it is far, the force is less. If it is nearby, the force is more. We know this law very well. So what the beauty of this, genius of Newton is that he just tried to see when we throw something in the earth and it falls, can we take it and apply to everything, right? So he generalized that law and came up with this gravitational law. So this has become a excellent universalization of the gravity. Then, of course, he did a lot of experiments with optics. We also saw that how optics was introduced in the curriculum last session. So Roger Bacon introduced optics as a curriculum in the university syllabus. So then that became a tradition of people looking into optics. The reason is like already people have this idea of whether we see it by light falling on something and coming to our eyes, or Euclid said, right? Euclid said that eyes send some rays and tries to capture it back. So that was Euclid's proposal. So people were interested in this optics, and then obviously came into this syllabus, and Newton did some experiments with this, and this is famous experiments. We all know that using prism, he showed that white light can split into multiple colors of this VIBGYOR. That is big. So that is because light goes into different angle when it passes from one medium to another. That's all. We will come, or we will not worry about that later. But Newton proved that white light contains multiple colors, and of course, if you combine these colors back, you can again get back this white light. So that is something that was not known before. Newton's experiment showed it. Another important genius of Newton is he did his own mathematics. All mathematics required, he invented that as well. The calculus which describes these motions, right? All these things he invented to do his physics. So he called these fluxions. That was the name. But later, this is replaced by our different formats. In fluxions, you have first derivative is f, second derivative f double dash. Don't worry about these formats and all. These are Newton's way of representing the calculus. So, lot of contributions from Newton. So anybody who is even barely know about science, they know about Newton because of his various such contributions. So he also mentioned that in spite of all this contribution, his famous statement is he could see very far because he is standing on the shoulders of giants, right? So such a statement from such a genius, right? Which is something that shows us how small we are, right? If Newton himself says that he stands in the shoulders of giants, then it shows that, okay, how much we are still to learn, right? So that is a lot of contributions from Newton. But Newton also went into a lot of controversies. For example, this calculus was invented at the same time during Newton's period itself by Leibniz, a mathematician called Gottfried Leibniz. There is a long conflict between Newton and Leibniz regarding who owns it. So somehow they kind of came to an agreement, but then it was not a easy resolution. But the world now uses Leibniz way of representing that dy by dx that we use in our calculus, right? That is how we use it. We discarded Newton's way of representing. We use this format. So that is one thing, a very nasty fight between these two giants. And then on studying light, Newton proposed that light is travel as part of particles. He used the word corpuscles. So Newton talked about light or imagined light as corpuscles, and he proposed this corpuscular theory of light. At the same time, there was another scientist, physicist, Huygens, who said it is not light is not particle, it is wave. So they were all, again in theory, they were debating. So this all was going on during the Newton's period itself. So that with that, okay, that's all there. Let's come to what signifies Newton's mechanics. So a lot of people like Laplace, Lagrange, and then people came after Newton. They took this as a major way to describe the world, and they started saying that when you know the configuration of world, say particles position of particles known at certain time, at t, then with the Newton's laws and all, it can be predicted how these positions of particles will be at, say, after some 10 seconds, 15 seconds, or even later. So the whole world is very predictable, right? Deterministic world. Newton's science gave a notion that the whole world is very, very deterministic. You can predict that, okay, this particles in this gas chambers are like this. After 1 hour, these particles will be there like this. Of course, you need a heavy computation needs, but in theory, it became a very deterministic world. And the idea of complete absolute space and time. The idea of space and time already exists for Newton, but Newton's laws did not depend on how the space is, how the time flows. It does not worry about these things. So for Newton is a religious person. For him, absolute space is something like God, right? So space does not change, time does not change for everybody. It flows same. All these things were part of, it's kind of a result of Newtonian mechanics, or we now call it classical mechanics, right? So that is, while that is all there, fine, this is all fine. But there is one major question was there. When two bodies attract each other, say, let's say mass m1 and we have m2, when it attracts each other, it has to either put a rope or some kind of connection should be there to attract or push, right? So when I want to push a stone, I have to use my hand, push it. Or when I want to pull, I have to probably tie it with the stone, pull it, right? But gravity between Earth and Sun, there is nothing in between. How is it pulling or pushing? Is gravity an action at a distance? That people started asking this question, right? There's something called principles of locality in science. When you cannot have something like a magic. See, this is like a magic, right? You cannot have something like a magic in science. You should know some connectivity, some cause, or something like that should exist for attraction, repulsion, increasing heat. You should have source, right? So those kinds of things does not exist in Newtonian classical mechanics. So that became a problem. But of course, mathematics of Newton works. People could predict the planetary motions um, to a reasonable accuracy, definitely. And then they were able to predict the cannonballs, projectiles. All these things are working fine. But this does not have a um, real scientific way of doing things. It still looks like a magic, right? So we will see the answer later, but it's for you to think about what could be, this could be solved. So principles of locality is fundamental thing in science, right? You cannot have something like a magic by just, people say, right? I just look into certain things, I can move it. Those kinds of magicians, or without just I can bend a spoon. Those kind of magicians and all are there, but that cannot be science. So you need to have a principles of locality. That's being answered later, but for now, for you to think how this could be solved, or who addresses this in this Newtonian gravity. Okay, while this is going on, people started. So we go into this 18th century, 17th and 18th century, where the industrial revolution starts. Industrial revolution is about how to use heat engine, and the fundamental technology behind is how to use heat engines to automate certain things, right? So a lot of experiments with the heat started appearing. People started theoretizing heats, heat engine. They started designing heat engine. All this work just to make sure the engines perform efficiently, right? How do we increase efficiency? We all know that how our capitalist system work, right? Currently, we know artificial intelligence drives a lot of things like that. At every point, some technology drives. So industrial revolution is driven by steam engine. So people started a lot of things, a lot of experiments related to understanding heat. Okay. So there is a nice theory, funny theory. When explaining heat, even including the chemistry's giant like Lavoisier, who is the father of chemistry, modern chemistry, he talks about heat is nothing but caloric. Caloric is a fluid. So they say that when heat spreads in a metal like this, in a metal bar like this, they say that some caloric is a liquid flows from here to here. So heat spreads like this. We still use this word calorie during our exercise routines, and we say how much calorie we burn, right? All these things come from this vision of a fluid flowing from fluid flowing in the body. That's how heat. That's what heat is. Heat is. So people started explaining heat, though since it is invisible, different nice theories started coming. So they started talking about a lot of experiments they wanted to do to get something perpetually, right? Without spending energy, can I do something? This kind of perpetual machines. This is a recent form, but the olden days they had perpetual machines. This is Boyle's perpetual machine. Like somehow you pull the water and push it back. It'll keep going on and on and on. This kind of perpetual machines they try to build. Lot of physicists, industrialists spend time, money to build perpetual machines, and they all know that somehow this perpetual machine would not work, and they came up with this, the thermodynamics law. So thermodynamics law is something like when energy is spent, when work is done, energy should be spent. You cannot get something done without spending energy. And it can be converted to different forms. Right? That is how we read this we read this first law of thermodynamics in the form of law of conservation of energy, right? Energy can either be created nor destroyed, but can disappear in one form, will reappear in another form. That is the form we see in our book. But actually, this is what the way that law arrived is through a lot of experience by these industrialists, scientists, and all. So that's how the people say that even including Einstein, Einstein said that this law of thermodynamics, especially the first law, can never be overthrown because it is not just some mathematics. It is not just some scientific theory. It is comes out of experience. Right? People spend they build that machine, they see the failure, then they arrive at this law. So that's why we cannot have one person assigned to this invention or discovery. It's Lavoisier, Sadi Carnot, James Joule, we know James Joule, of course, Jules Landau we have read during the college days. So different people came up with this thermodynamics law. So that is how that is how this law is. So it is becoming it became a cornerstone in physics. So if you come across any invention, say you discover something, you came up with the equation. If your equation for some reason violates thermodynamics laws, then immediately people will reject it. So this is how the first test of our the proposal experiments, whatever we tell in physics, if it violates the thermodynamics laws, then it violates, it becomes magic, and you cannot put it as form of a scientific law, will immediately rejected. That is how that is the law, that is how these laws are important. Okay. So then there is another thermodynamics law comes into place. These are all happening during the industrial revolution as it happens. As people read more and more about heat. So that second law of thermodynamics is also something like out of experience we know. Heat flows from higher temperature to lower temperature. We know this law just from experience, right? You put a cup of tea, the cup of tea which is hot, with a few minutes it will become cold. We know that. When I initially knew this law, I was wondering why should we have a law for this? This is so obvious, right? But what comes, why this law is so important is when you do some work, heat is expended, right? Again, if you want to get the heat, so work done, heat is expended. Can I put it back, this heat? Can I make this system reversible? And then get the heat again, use it for work. Reverse the heat emission process so that from the environment heat can be absorbed and work can be done. Can this happen? That is the attempt they tried, but that cannot happen. When you want the heat to be given to a system, you have to work. You have to do additional heat. You have to somehow do some work to get the heat generated, right? You cannot expend the heat by doing some work and do a reverse process of absorbing the heat back. Irreversibility. irreversibility is there. It's a fundamental thing in the nature, right? So that is what this second law of thermodynamics talks about. So that means heat flows only from hotter places to colder place, right? So they coined the term called entropy, which talks about energy unavailable to do work. In nature, once you expend some energy, you cannot reverse it. It is not available to do further work. In nature, it always increases. So we have this idea continuously improve, and Boltzmann introduced entropy to.
Add a small, sorry to interrupt. This is Prasanna.
Yes.
Just to add, when you mentioned it moves from higher temperature, lower temperature, this is actually a parallel to the time also, the concept of time, which is a very philosophically interesting connection.
Yes.
Because there, we always think that we can always, still like perpetual motion, we keep fantasizing on time machine where we can go back in time. So this law nicely shows why it is one dimensional. I mean, one directional.
One direction. Yes. Yes. Yeah.
Maybe I will leave debate for later time, but then it nicely shows that why time is one directional.
Exactly. I was about to come.
Oh, is it okay? Okay, please.
Yeah. Yeah. So yeah, that's what. Yeah. So now that Prasanna brought it up, in physics, all equations, if you see, including Newton's law of motions, Einstein's later gravity, sorry, his Einstein's transformation, all this special theory of relativity, everything, they do not have a sense of time. So say the equations may have time. If this time can be instead of t, if you put minus t, equations will work. That means the time can go in this direction or in this direction according to those equations. I'm not going into that equation, but that is a possibility. So in all other physics that we know, time can be reversed, right? But only the second law of thermodynamics says that this is definitely not possible. As time flows, heat always goes from one direction to another direction. You cannot reverse it. So time is also not reversible. So that is the importance of this equation. So that said, and then the entropy is the term. Thanks, Prasanna, by the way. Yeah. So yeah. Entropy is something that is the word is used by a lot of people. We will even use it, we even use it in computer to talk about the randomness, right? So that's all comes from here only. Boltzmann took this idea of entropy, he linked it to probability and told that entropy is the measure of disorder. Measure of disorder, right? So that means, so it's continuously, the world is going towards disorderliness. If we put together our room in an orderly fashion, so we arrange all desk, book, everything. In over a period of time, by naturally, it is you would have taken a book out, you put it back, put it in some table, some other place. It's all going towards disorderly. The entropy is a measure of that disorderliness. So that is another way of talking about entropy. So this is all maybe little difficult for non-physicists. Please stop and ask questions if you are not clear. So entropy is about measuring disorderliness. That's how people took it and coined this. I mean, this is a nice term, evolved over a period of time. We will talk about entropy in computers also later. Again, these are different people's experience and contributions. So we cannot attribute second law of thermodynamics as well to just one person. So these people and all have contributed. So a lot of as industrial evolution progresses, the idea of heat became a center point in physics, and that kind of became a I mean, it evolved as a this important law. There is the third law of thermodynamics as well, which we are not going to talk about it in our class. Okay, so it's so important. Heat became so important that someone I read somewhere that if you understand heat and light, you know half of the physics. More than 50% of the physics you can understand. That's what I read somewhere. So such an important thing, these two. Okay. So heat is further described as a finally caloric and all is not there. Boltzmann put the final theory that it is nothing but a kinetic theory of gas. That is, heat is collective motion of atoms in gas or any material. Right? It's a collective motion. So that means when the atom vibrates, in any metal or any body, when atom vibrates, we have heat. Heat is motion of atoms, right? So that theory, they when it is moving fast, then it's very hot. When it's moving slower, it is very cold. It is going cold. What happens? The atom stops. If we can stop the atoms, that is called absolute zero. We say that temperature is absolute zero, right? That means it is atoms do not vibrate at all. They try to stop it. You keep removing the heat from a body, you can continuously slow down the atom and you can make it absolute zero. So that means that you cannot go lesser than this. You cannot have a negative action, right? Negative movement, negative motion you cannot have. Only you can have up to not moving at all. So that's a zero motion. The moment you arrive at that, it's called absolute zero. Lesser than that, there is no heat possible. So that's the way they moved, and that is the idea of absolute zero. So heat is concluded as motion of atoms in the body. Okay, so that is how that idea evolved. So while this is all going on, we have things working in the magnetism and electricity as well. The idea of magnets are there for a long time. Magnetic materials are available in nature. People were toying around with it. It's all going on and on and on. And electricity also has come. People saw charged particles by rubbing a silk with some plastic. You can see it attracts things, and they have an idea of charged materials and all, right? So, but eventually, um, they slowly recognizing this, they were recognizing that they somehow integrated. They were fighting each other, but Michael Faraday realized that, or demonstrated that, if you have a coil and there's another magnetic material, if you put here like this up and down, it can generate electricity, right? So that's kind of way I mean, the experiment shows that electricity and magnetism can or be very related, can be interrelated phenomenon, interrelated, or one creates another. Right? Either you do that or you send the electricity through this and it can be moved. So that is a very simple idea gave to so many devices, right? Motor, dynamo, Dynamo is, you give mechanical energy, it will convert electrical energy. Again, you have a magnet. We have magnet, something rotation, coils rotation inside the magnet, you produce electricity out. But if you do this electricity, if you give the electricity in, then it will produce the rotatory motion, and that can be used as a motor. Right, so this kind of gave one nice experimental way of showing that induction is something that is possible with electricity and magnetism. This fight is going on between these people working on magnetism, people working on electricity. That okay, which is primary, which is more important, right? So they Michael Faraday experimentally concludes that, oh, okay, they are all interrelated and we can benefit if we all work together, right? So that's an idea also coming up during this period. And a beautiful contribution is from Maxwell. James Maxwell saw that, okay, this electricity magnetism is there, but I want to, or he created something called uh, wave, which talks about these two, right? Electricity and magnetism as a, he put it together as a one single theoretical framework called electromagnetic theory, right? That kind of one of the famous integration in science. Electricity and magnetism in one theory explaining what these two are all about. So he usually, this kind of theory, especially when we say this field, we will come to the field later. But when we say wave, it is always, wave has a velocity, right? Wave has a velocity, wavelength, and frequency. All these things is there. So when they calculated the velocity of the wave equation, Maxwell proposed that velocity came to the speed of light. There starts a debate, right? Already we saw that Newton proposed corpuscles. Now Maxwell says light is wave, because his wave equation, when he arrived at the speed of that wave equation, it appears to be matching with the constant part appears to be the matching with the speed of light. So it's during the Newton's time, since Newton was a giant scientist, Huygens was ignored. Corpuscle theory was taken as a final verdict. People kind of accepted. And then in between, there was another important experiment done by Young. We have all read it, called Young's slit experiment, which proposed light as the experimental verification that light as wave. And then we will see that experiment quickly if time permits. Then we have Maxwell equation says that light is wave. So this is in theory. Even theoretically proved that light is wave, right? So light is really particle or wave. This debate is going on and on, right, for some time. So before going further, we will understand these two ideas. If you see Newton's time, everything was force. But later, people already, as you said, we already talked about, or the world already knows magnet. And magnet has some kind of, if you see nearby, if you put a pin, it will just attract, right? So how does it exhibit something, some attraction and all? when something is put here, something put here, right? So it people we can understand, for simplicity we can understand, it's a this kind of area is a field of influence, area of influence. So that they call it as a field, right? This area where it influences something is called as a field, all this area. So this idea of field evolves during this 1700, 1800. That's how FSC James Maxwell used this idea of field, constructed the wave equation, and told that wave is light is wave. But this field has a lot of influence in different areas. We will also quickly talk about what is wave. I just put this together because when we usually do it for non-physicists, this will be helpful. So please let me know if it is too simple, we can ignore. But wave is nothing but vibrations that transport energy. Okay. When we say wave equation, or when we describe energy of a system, it will be usually a wave equation. When we say, okay, energy is going forward this direction, something like that, when we say, we actually in physics, what they mean is there's a wave equation which carries that energy. Okay. So that means when something vibrates like this vibration is given here, given to the next particle, given to the next particle, like that it goes on. That means that vibration is given means energy is given to the next particle. So that is what wave carries. Wave carries energy. Wave carries its wavelength, wave has its wavelength, which is one successful wave, length of one successful wave. And it has its amplitude. That means how far it goes. When it vibrates, how big is this vibration? So this amplitude, wavelength, and frequency are all properties of wave. Frequency is how many times it vibrates per second. So these are all some fundamental nature or properties of wave. Another important property is wave has interference and diffraction. Interference is mix and match. I think I have a picture here. Yeah. So when two waves put on top of each other, you put this wave on top of each other. When this part meet this part, that is, it will be more higher, right? It will be more higher like this. When this part meet this part, it will be plane. Okay. So this is called constructive. This is called destructive. So it will be much low here when this part and this part meets. I mean the lower and lower meets. So this is called interference. Waves form interference, right? When you see two waves in the water, you would have seen something like this. So this interference, high amplitude, low amplitude, right? So this is a property of wave. Don't worry about how amplitude goes high. What is what is that exact amplitude, size, and all? It is just that understand that it is a property of wave. That means there are possible of high amplitude, low amplitude based on the interference point. Okay. So that is nature of wave. Because this is all needed for the next next coming sessions. So while this is all going on, as we said, we want to understand the heat better. So people were experimenting with heat. And there is one thing called black body radiation. Black body radiation is you keep heating some material. It goes hot, it keeps on increasing. It becomes red, hot, blue. When it is very hot, it becomes white, right? But it has some energy in it. It will keep giving energy back, right? That's called black body radiation. Don't worry about the name black body. It is not actually black. Basically, it is about analyzing what comes out of a hot body. Okay, don't worry about the color. So analyzing what comes out of a hot body. So while analyzing this, people were doing, of course, if you see when energy, when what comes out of radiation means radiation is emitted in form of energy, right? When energy comes, it is in the form of wave. It is usually described as a wave because waves only transfers energy, right? So when it comes as form of energy and its form of wave, it is a continuous process, right? A wave is continuous usually. It goes like this continuously. But as number of the energy keeps on, they were measuring this energy, and at one point they found that the equations does not match, the prediction of the equation does not match the output of the or the measurement that comes out here, right? Emission, the frequency, the prediction of the equation does not match the emission, right? So Planck analyzed this, why this is not matching, and it came up with a very reluctant equation like this. Instead of wave equation, first time in physics, energy is equated like this, not in the form of wave equation. It just said energy is equal to frequency, and this is something called Planck constant, which is very small number. So what he says is energy can come only in the multiples of this number. You cannot have, say, if it is one unit, you cannot have 1.5 unit. You can only have multiples of h nu, h frequency. So 2, 3 like that. So energy comes in pockets. You cannot have intermediate particles. He named it as quanta. Okay. So energy, people thought that energy is always a wave equation. It's a continuous thing, and you can have any measurement. Yeah, I want less energy, you can go very less. I can more energy, you can go very more. But at one point, the measurement does not observe or match the observation. They are forced to look into that energy is discrete. That means it comes in packet. That is like saying that you go to a shop, you ask for this shop owner, okay, a sweet shop, I want 1 gram packet. He may say, okay, I always give 1 gram, but if you cannot give, I will not pack half gram, right? So I will give only in 1 gram, 2 grams, 3 grams, right? You have some Mysore pak, you cut like this, right? Only single piece. Your mom says you can take only this piece, this piece. You cannot take 1.5 piece. You cannot come in this measurement. You can take only this piece or this piece, which is in a very standard size. Energy is emitted in this standard packets size. That is what is meant by quanta, and was analyzed and done by Max Planck. Introduced this simple equation, but it started, he did not know that what is the consequence, but that started something called quantum physics. Any questions so far? Or is it too much? Looks like people are talking.
And just one small addition to it.
Mhm.
The quanta can be mathematically equated to integers actually, because integers are like whole numbers,
Right.
and anything in between is fractions. So
Mhm.
usually the wave is a continuum which is existing. You can walk along it. Integers
Mhm.
means it's like having holes in between. You have to jump one number to the other number.
Yeah. Okay. Yes.
So this is a very classical way of, mathematically equating it to a continuum versus a discrete system.
Okay.
Very nicely, at some point, a continuum becomes discrete and discrete becomes continuum is a classical example. Seeing it as a wave up to some point, suddenly it turns out to be a quanta.
Yeah. As it go further, smaller and smaller, it becomes quanta, right?
Yes, yeah.
Yeah.
Just wanted to.
Yeah. Thanks, Prasanna. So that is quanta, introduced in 1900. Further down in 1905, we know what Einstein did. So he 1905 he did this, published this famous 4 papers. So photoelectric effect is when light falls on a plate of a metal plate, it emits electron, right? Which means it's like light, like a bombarding particle. Because wave cannot emit or dislodge an electron, right? But light falling on an atom, so it has an electron, it dislodges it and produces an electricity. So that is the photoelectric effect published by Einstein. Again, adding fuel to the fire, Einstein says that light is particle. So Einstein used his idea proposed by Max as a the quanta idea, which we just saw. He used it and called the light particle as photon. So we know that Newton said particle, and then Young's Reed experiment said wave, and then we know that Maxwell gave it in theory that it's wave, and again Einstein says it is particle. We also know that at that time Einstein did a excellent special theory of relativity, which talks about so this is relativity and all. That itself is a separate session. But we want to just quickly see that because the idea of absolute space and time is overthrown by special theory of relativity, that because two things is measurements are related to the velocity of measured and measuring persons, right? Or the how related, how is how is the related speed between them? So when something is traveling like this at a particular speed, as yes, when I am also traveling at the same speed and I am measuring its length, it appears normal. It will appear normal. Or when I am in Earth, my friend is in Mars. When there is a star burns here or explodes, I say it is at 6:05 p.m. My friend says, no, it is at 7 p.m. Right? So both are correct because light took time to reach here and light took different time to reach here. Right? So he measures it at 7 p.m. I measure it at 6 p.m. The only constant is velocity of light. All other things are relative. That is what relativity is all about. So when you are traveling related to another object, all your measurements are not as before. You have to measure, how to say it, you have to measure, you have to correct your measurements, you have to correct your scale. That's what relativity is all about. So basically it is saying that your time of 1 second is not 1 second always. Your space of the way you see it now is not same as you travel or go in a different directions, right? So that is one. We will come a little bit more on this little later. And we have this another excellent equation, right? We know famous Einstein's equation, mass energy equivalence. This is very famous. Another integration, like Maxwell's integration, which talks about electricity and magnetism. Einstein's equation talks about energy is nothing but it is mass, which can be converted to energy in some ways, right? So given a proper condition, energy can be converted into mass, mass can be converted into energy. So that's a famous equation we know. And he also gave an explanation of Brownian motion, which is again confirming atomic theory. So a lot of changes started happening from these papers. Again, if you see, it's revolutionizing ideas. Planck already gave a made enough damage, saying that energy is in discrete form. And then Einstein added another fuel to the fire, saying that light is particle, and gave that everything is relative, and energy is nothing but can be converted into matter or vice versa. So this all made a lot of problems to the physics, because everybody thought that after Newton, physics is kind of very stable. That is all people thought, but then this all probably damaged now. Any question on this? Maybe too much physics? People are dropping.
No. It's enjoyable, but oh yeah. Right now, I am also seeing the participants.
Yeah. I've been monitoring. Okay. Probably we'll stop here today.
Yeah, fine. Yes.
Yeah, we'll continue in the next class. Hey, Judah,
Yes, sir.
can we start with evolution theory next class? I want to talk about two discoveries. One is evolution theory by Darwin, and another is Mendel's law of genes.
You want to combine them or split them as two separate things?
Combine them in one class if that is possible.
Sure. I'll
Yeah.
also do a little bit of history of biology, like for example, Robert Hooke and all.
Oh, that will be good. Yeah, that will be good. Because maybe too much of physics probably makes people bored.
No, actually, the thing is, all of these things are interesting because also because of the experiments. Like, for
Yeah.
example, the special theory of relativity came as a response to there was a guy called some M&M fellow was there. They were basically doing research with the satellites, and they found out that the speed of light is constant, and that's the upper limit. So nothing made sense. For example, if you are going on a 20 kilometer per hour truck, and if you're shown a laser, it should be C plus 20, speed of light. But it wasn't like that. It was always C. It was always a constant.
Yeah.
So special relativity explained that.
Yes.
So in context with how the discoveries were found with the experiments, it was like a constant. Everything was during that time in physics. Everything was contentious and controversial. So
Yeah,
even Planck didn't like what he was saying. What he himself was
yeah,
saying. Then
yeah,
Albert Einstein was against quantum theory. So it was,
yeah, yeah.
although they kind of built it up. So
I
it's
want
very,
to I want to bring up this Michelson Morley's experiment as well.
yeah, exactly.
But I thought that may be too much physics, and
Right.
then I thought just have a glance of what happened as historical events. Um,
Right.
so it's better to have one small deviation from the flow
Yeah,
by introducing the biology part of it, because that was
definitely.
also I wanted to anyway discuss. Almost we are at the same time, right? During this 1800,
Right.
yeah, Darwin's principle. We can talk about it and then continue this.
Sure, sir. I'll try to get something done by next week.
Okay.
I'll speak with Darren.
Mhm.
If he and I are willing to co-host that lecture, we can do that. Otherwise, I'll present.
Sure. It'll be great. Okay. Yeah.
Okay.
So basically, I want to, I have more slides, but we can do it to next class. So I want to go through this Einstein generalization and then Bohr's model of space quantization. So he quantized the space, and then how this war of wave and particle kind of settled by de Broglie's wave equation and finished there. Of course, a little bit of quantum and finished there. Okay, so probably we will start with Darwin next class, and then if time permits, we will continue on this.
Okay, sir.
Okay, yeah. Any other question?
And just one observation is all these people then they had not segregated themselves like presently we do mostly like engineers and so they were more of ready to accept even a few magical things like you mentioned that calorie was seen as a fluid and you may be knowing that ether was also considered as a fluid.
Yeah.
So likewise, though their imaginations were not so proven right later, but that helped the progress in many ways. Like you are showing that now the Rutherford's model, and, where they assumed it's a discrete ring.
Yeah.
It was disproved and then proved again. So it keeps oscillating between the wave particle as we go. Very interesting to understand and enjoy these things.
Yeah, excellent. Yeah, I also when I understood this de Broglie wave equation, the question like, will an elephant have a wave, right?
Yes.
Chasing that idea and understanding was very interesting to me. So yeah, we'll take it further. I don't know how much people will like it. Let's see.
Since it is being recorded, I think people should come back later. As they...
Hopefully, yeah. Okay. Thanks, everybody.
Thank you.
Thank you. Bye.
Thank you.